Good evening, everyone. Welcome to the Simons Theater at the New England Aquarium on a beautiful night. Thank you for joining us. We are here for the John H. Carlson Lecture, which is an annual partnership, and I'll mention a little bit more about that in a minute. Very excited to have our colleagues here from MIT. Tonight's lecture is Greenland Ice Cores Tell Tales of Past Sea Level Change with Dr. Dorthe Dahl-Jensen. The New England Aquarium has a lecture series that we show to the public for free that's sponsored by the Lowell Institute. And this is part of that lecture series, but once a year, we partner with our friends at MIT for the Carlson Lecture. So excited to welcome you all here tonight. Specifically, we're partnering with the Lorenz Center of Department of Earth, Atmospheric, and Planetary Sciences at MIT, which I think many of you know. Tonight's event, in addition to being sponsored by the Lowell Institute, is part of our lecture series, and we have different lectures. We'll be talking a little bit about the next lecture in our series, which is November 13th at the end. My name is Dr. John Mandelman. I am the Chief Scientist here at the New England Aquarium and also our VP of our Anderson Cabot Center for Ocean Life, which is our applied research arm of the New England Aquarium. Many folks don't realize that the aquarium is much more than our amazing exhibits. We do a lot outside the building too, towards a healthier ocean, and the center is pivotal in that. It's also a pleasure to welcome all folks joining us virtually for the lecture tonight. Thank you for coming, so to speak. The Aquarium at large is a nonprofit organization. We've been protecting and caring for the ocean for over 50 years. We were formally launched in 1969, or open to the public in 1969. We share our ocean conservation mission with more than 1.3 million annual visitors who come to the aquarium each year with the goal. Our goal is to inspire them to love, respect, and act on behalf of the ocean. Another way we protect the ocean, as I noted, is through our research arm, the Anderson Cabot Center, and all the conservation work that we do beyond the walls here in the Gulf of Maine and around the globe. We've been studying the ocean for decades, and we know through our research and the research of many, many others that the impacts of climate change and other human activities are having a major effect on the ocean. Our work at the aquarium and our center helps inform actions to help protect the ocean through working with policymakers and working with different industry groups. We also work to help and create a more resilient and welcoming waterfront for Boston and beyond. Tonight's speaker, Dr. Dorthe Dahl-Jensen, shares our passion for the ocean. She has dedicated her career to the study of the history and the evolution of the Greenland ice sheet and the mechanical properties of an isotropic ice and ice in the solar system. Here to tell you more about Dr. Dahl-Jensen is Dr. Dan Rothman, Professor of Geophysics and co-director of the Lorenz Center at MIT's Earth, Atmospheric, and Planetary Sciences Department. Dr. Rothman, welcome.
Thank you, John. The John Carlson Lecture is an annual public lecture sponsored by the Lorenz Center at MIT. We'd like to thank the Aquarium for hosting this event, which makes it possible for us to bring the excitement of basic climate science beyond MIT to the general public. And we are especially thankful to John Carlson, who is with us tonight, for making this lecture series possible. The Lorenz Center is devoted to learning how climate works. One of the many ways to do that is to study the role of ice in climate and sea level change. The ice sheet that covers nearly all of Greenland is a major focus of such studies. Tonight's speaker, Dorthe Dahl-Jensen, a professor of glaciology at the University of Copenhagen and the University of Manitoba, is one of the world's leading experts in this field. When the climate warms, the ice sheets that cover Greenland and elsewhere can melt, causing sea level to rise. But how much? And how can we know? By leading field expeditions to Greenland and carefully analyzing the data they obtain, Professor Dahl-Jensen has shown, for example, that during the last period between glaciations, when Greenland's temperatures rose by about 5 degrees C, the thinning of Greenland's ice sheet caused global sea level to rise by about 2 meters. Such fundamental observations greatly advance basic climate science. They also make invaluable contributions to understanding the impact of global warming on the Earth system. For these efforts and others, Professor Dahl-Jensen has received many awards and prizes. I'm certainly not going to mention them all, but I would like to point out that she has even been knighted twice, right? First in Denmark and then in France. We're delighted to have her speak here at the 12th annual Carlson Lecture. Now, finally, we'd like to ask you to save your questions for the end. And when we get to the end, we'll be especially interested in receiving questions from any pre-college students that are in the audience, and we'll give them priority at that time. So let's welcome Dorthe Dahl-Jensen.
Thank you very much. And thank you so much for inviting me to come. And thanks for showing up. I hope I can give you a good lecture here. So before I change the slide, I just have to say that the layers you see there are dust layers from ice that's more than 20,000 years old from an ice sheet. So I've been introduced so nicely already. So the only thing I can add to that is that I've worked with ice core my full career, and it's never ceased being very, very exciting. So now I'll just show you something very special first. I hope it works. So I find ice is very fascinating. It has the unique properties of having a floating form on water, which is the conditions of life on Earth. So it's very unique, and on top of that, it's always also extremely beautiful. So this is my fascination of ice that I have had for all my life, and I think I'll continue to have it the rest of my life. The music was from called Blue from Terje Ingusat, who's also specialized in only playing on ice instruments. And we had him visiting our camp, giving a concert, which was shown in the US and Norway from 3 TV channels. So that was rather amazing. But now back to the facts. So what I'm going to talk to you today is first about what is happening right now. Well, how is the climate changing? And after that, I'll take some examples from the Greenland ice cores, telling about what happens in the warm climate, what happens in the cold climate. And finally, I'll show you some pictures from our recent camp, EastGRIP, in the northeast part of Greenland. So on this picture, you see a little autonomous ice core box that we're trying to get to measure on the ice cap, but it's observed by the Skidoo because it's under training. So first I'd like to say that doing ice core research requires very big teams, very big international teams. So what I'm going to present for you today is not my work, it's the work of the whole team. So I'd like you to remember that when you hear all these stories here. So the vision from our group is to understand and get an improved understanding of especially the warm climate periods by studying ice cores and developing models to explain observations and predict how ice sheets respond to climate changes. And on this picture here, you can see a little thin piece of ice with a lot of small air bubbles in. And in these air bubbles, we have trapped air from the past atmosphere reaching more than 100,000 years back in time in Greenland and 800,000 years back in Antarctica. Because when snow, the fluffy snow, is pressed together, the air bubbles in the snow is trapped in these air bubbles. So this is one of the things that is super unique in the ice cores, directly to have past atmosphere samples. So the work we're doing is very, very multidisciplinary. Because here we are, standing on the middle of the ice sheet. We have to take care of building the camp, as you can see. We have to develop the drills and drill the ice cores. We have to store the ice cores. We have to talk to the pilots of the Hercules with skis on. And here you can see them taking off from our skiway, sometimes using rockets to get enough speed to leave the skiway. And also, we develop the drills. We have engineers in our group that does that. So our group needs all these skills to be able to lift the task of drilling these deep ice cores in Greenland. So first, I'll talk a little about the climate. And this is a movie starting in 1880 and showing how the climate has changed since then. And I want you to observe that global climate change is not just the same everywhere. You see some places it's warming, you get the yellow and red colors, and other places it's cooling, you get the blue spots there. So it's not just uniform, but as we go towards the present, which we have reached now, you can see it's really warm in the north, in the Arctic. So clearly the ice in the Arctic is melting right now because it's warming so much. Globally, it's warm 0.2 degrees Celsius, but over Greenland, the warming is 2 to 3 degrees. So a lot more than the global values. You can see in Antarctica, it's a little more mixed. So right now, it is the Arctic glaciers that contribute most to sea level rise, but that will also change. So since, I just tried to find some facts about Boston. So since the pre-industrial time, the temperature has warmed 3.5 degrees Fahrenheit over Boston, which is 1.9 degrees. And of course, you've prepared this visit very nicely for me, because we had record temperatures the day I came this Monday. I heard they reached 83 Fahrenheit, and the last time it was so warm was in 1920, when there was 82 Fahrenheit. So thank you very much for that. So when you have this big warming, you also have sea level rises. And the satellites that measure the elevation of the sea has really changed our understanding on sea level rise. So here you see a map showing the change of sea level rise since 1993 to 2012. And again, you can see some places it's blue, the sea level is actually dropping, and other places it's up to purple, where the sea level rise is up to 9 millimeters per year around the small islands in the Pacific. The main sea level rise right now is 3.5 millimeters per year. And if we look at, again, what happened in Boston, I read, and I don't know if it's true, I just read it, that there's been 1 inch of sea level rise for every 8 years, and it's predicted that during the next 15 years, there can be a rise up to 6 inches. But then I'll go back to more solid ground and talk about Denmark, because when you look at the predictions in Denmark, the predictions are that the sea level will rise 70 centimeters, but with an uncertainty of 60 centimeters. And that's actually the most dangerous uncertainty ever, because it's telling you that the sea level rise can be between 10 centimeters and 130 centimeters. And as it is very, very expensive to secure a town towards sea level rise, you know, a more precise knowledge would be amazing. And that's part of the reasons that we work with the glaciers to understand how much melt there comes from the glaciers, because this will be the greatest contributor to sea level rise in the future. So I've tried to show some statistics here. We have the Intergovernmental Panels for Climate Change from the United Nations that makes these big predictions on sea level rise. And here you see the development of these predictions. So you can see back in time, the predictions was that the sea levels didn't really contribute to sea level rise. But as time goes, you see that they predict more and more loss of mass from the ice sheets, but you can also see that the bars get bigger and bigger. The uncertainty gets bigger and bigger. And isn't that a strange feeling? You're a researcher, and you research and research, and as a result, the uncertainty increases. You know less and less. So you realize that you actually don't know a lot, so you need to learn more about it, so we can decrease the uncertainty of these estimates. So here is just a little overview of where the water is coming from. And you can see that this is from 1993 to 2004, where the mean sea level rise was 2.7 millimeters per year. And you can see that Greenland is a small slice, Antarctica is a small slice, and the glaciers is a little bigger, and the thermal expansion is a lot. But you can see that the contribution from the land ice is set to 47%. So if we go a decade into the future, 2004 to 2015, you can see the sea level rise has increased to 3.5 millimeters per year. But look at how much Greenland has increased during this time. So right now, Greenland is actually the awakening giant who's going to give the very big contributions in the next decades. And then Antarctica will come too, is our prediction. So if we look at how much ice we have on Earth, we can see that if the whole Greenland ice sheet melted, could give us a global mean sea level rise of 7 meters. Antarctica is 10 times bigger and can give a sea level rise of 73 meters. Ice caps and glaciers that probably will melt during the next 100 years only will contribute 0.5 meter to sea level rise. And of course, the sea ice that you're seeing on these movies here during the years means a lot for the temperature and the reflection of the sunlight, but they don't mean anything for sea level because it's already floating on the ocean. So I'll just talk about Greenland in this talk. And here again, we come back to the satellites, the GRACE satellites that observe how the mass of ice over Greenland is changing. And you can see every winter you build up mass, and every summer you lose mass. But in general, you can see that we are losing mass from the Greenland ice sheet. Some years more than others, but in general, it's going down. And if we look at it, through the whole period that the satellite has been measured, we see that there's about 281 million tons each year, which corresponds to about 0.8 millimeters. And that's of the 3.5 millimeters we have now. But it's still the fact that it's only 0.01% of the volume that's melting each year. So Greenland is super vast, and it'll take a long time to melt, even with the rates we have today. So now let's turn to the ice cores and what they can tell us. And I'd also like to let you know that I don't have any clock to look, so you have to shout when I talk too long time, because I don't know how the time is going. So one thing we always argue is that we're not fortune tellers. We're not telling about the future climate. We're not modeling. We're not predicting. No, we are wise men because we're looking into the back. We're looking back in time to things that have happened, and we try to learn from this and gain understanding that can help us into our future. And I think that's really important. So we drill the ice cores. We have our ice core drills. They're very special. They're made for ice core drilling. And I have a plot of it here. The instrument itself is 13 meters long, and it's hanging in a cable. When we lower it down to the bottom of the borehole, and we drill ice cores that are 3.5 meters long with a diameter of 4 inches. And we drill, and then we pull the drill up, tip it to the horizontal position, take the ice core out, and repeat. And we try to reach depths of 3,000 meters in the Greenland ice sheet. And it normally takes like 2, 3, 4 seasons to drill a full ice core from the top to the bottom, and we only work in Greenland in the summer months. Come back and teach our students and do research the rest of the year. So the drill head, you can see here, it has 3 knives at the bottom. So basically it's like an ice screw. You simply screw it down into the ice until you have the 3.5 meter of ice inside the core. And then you can see the 3 bronze core catches. When you pull backwards in the cable, they flip in to the ice core. And when you pull backwards, you break the ice core in the bottom, and then you pull the ice core up. So in that way, it sounds very simple. But of course, as with most things, there are always things that are difficult, because you can't pull a drill up and down a hole if there's not some freeway. The ice core has to be a lot smaller than the hole. So you're producing a lot of ice chips, and you have to spiral them up and collect them in a chamber, because else you'll just clog the hole with ice cuttings. That's the real trick to get that to happen. So this is just a picture from our science trench. And normally we are people from like 14 nations working together. So there's not 2 people here from the same nation. And you can see that everyone is running around and helping each other. So first we cut the ice core in the many samples we need for all the analyses that will happen. And you can see how people run around and help each other, always running around and helping each other. So that's really cool. We measure the visible stratigraphy, very much like the picture you saw in the beginning of the Milky Bands. And then finally, we save the ice cores and cut a lot of samples, like a post office that we send off to the probably 50 groups that work with the ice core samples when we send them back home to the labs. So this is what we produce. We produce climate records going back in time. And if you look at this plot, you can see it starts at 0, which is present, and then it goes back to 140,000 years before present. And this is how we always present things going back in time. So you have to get used to that on the figures here. And you can see that, I don't think it'll work, that the first 11,000 years is our warm interglacial period, the Holocene. Then we have a long period with cold temperatures from the glacial time, where you see there's a lot of wiggles up and down, abrupt changes. And at the bottom of the Greenland records and deepest down, we have the ice from the previous interglacial, the last interglacial, also called the Eemian. And you can see that this period is actually much warmer than our present period. So this is the thing we have studied a lot. What happens when it gets so warm? How much of the Greenland ice sheet will actually melt away? Well, how much melted away in the past when we had a period that was more than 6,000 years, where it was a lot warmer than today. So this is the first case, the first story I'll tell a little about. So the analyses are never very simple, but I'll try to explain this. I think it's probably one of the only real curves I want to explain to you, so I'll take my time. In the top, you can see the stable water isotopes, which tells us about how the temperature was back in time. So the further up you're on the axis, the warmer it is. The further down, the colder. And you can see the white curve is the measurements, but then we correct for upstream effects. Where did the ice come from? Where did it flow from? And then we get the red curve, where you can see it was 8 degrees warmer at the onset, and then it cooled with time. In the middle, we show how much air there is in the air bubbles in the ice, because this is a proxy for the elevation. You all know the air is thin if you go up on a mountain, and when you go down to the ocean, there's more air. So we can measure the air concentration in the bubbles, and we see that as we go through the Eemian from 130 to 115,000 years, the concentration of air goes up, because you can see the scale is the opposite way. So the elevation is dropping, and if you try to translate that to elevation change, you have to use a lot of tricks, but the end is that the ice sheet was 220 meters higher than the present when we started, going out of the previous glacial period, and then it dropped 200 meters below the present at the end. So we had this drop of 330 meters, and this is elevation, and we also get reactions from the bottom. So it probably lost about 400 meters of elevation during this period. So when we run our models and look at this, the result is that the Greenland ice sheet reduced its volume with not more than 25%, which is equal to 2 meters of sea level rise. So even though it was warm for a long time, we didn't lose the whole Greenland ice sheet. And I think that tells that the Greenland ice sheet is rather resilient, and it will take time for the ice sheet to melt, even in a warmer future. So the fact is now that we have drilled many ice cores over the Greenland ice sheet. And I tried to show them all here, from Dye 3 in South Greenland to Camp Century in the north. And I've shown the stable water isotope curves there too, in such a way that they are on a depth scale. And the lines, the blue lines show the present temperatures. And what I want you to note is when you get down to the bottom, in all the ice cores, you find ice that's warmer than the present. Sometimes it's folded and disturbed, but it's always there. And that shows us that all over Greenland, from north to south, there's been ice from this Eemian period. And of course, this gives the obvious conclusion that there was a big ice sheet over Greenland in this time. And I can't show it better than this movie from NASA that I'll show 2-3 minutes of, so you have a break listening to me.
For decades, scientists have been probing the Greenland ice sheet from the ground, air, and space. Now a new study uses those observations to see within the ice sheet, laying bare a tale more than 100,000 years in the making. When we look inside an ice sheet, we can see distinct layers formed by thousands of years of snowfall. As snow accumulates, these layers get progressively compacted into ice, which then flows under its own weight. To get a precise history of a particular spot on an ice sheet, scientists drill into it and recover ice cores, which provide a record of the ice's age and what the past climate was like. Seasonal variations, along with ash from volcanic eruptions, show up in the cores, allowing us to date the ice and correlate samples from different sites. To extend this age information across the ice sheet, the best tool that we have is ice-penetrating radar, mounted on aircraft flying low over the surface. Radar transmits electromagnetic pulses into the ice and records the reflected signals, allowing us to track the depth of the layers detected in the ice. Since 2009, NASA's Operation Icebridge has flown over Greenland more than 100 times with a wide variety of instruments, including radar, and produced vast quantities of data, adding to the work from many other missions. This has allowed researchers to generate a three-dimensional map depicting the age of the ice throughout the Greenland ice sheet. This 3D age map shows that 3 distinct periods of climate are evident within the ice sheet. The Holocene, shown here in green, the last ice age, shown in blue, and the Eemian, shown here in red. The top layers from the Holocene period formed during the last 11.7 thousand years and are fairly flat and uniform, though the thickness varies depending on how much snowfall occurred. Below this, deeper within the ice sheet, we see layers that formed during the last ice age. Layers from this period are darker and more complex, having been further squeezed and sometimes folded as they flowed over the rugged bedrock below. Deeper still are layers of ice left over from the warm period before the last ice age, more than 115,000 years ago. Eemian ice can reveal how the ice sheet responded to a period of warmth similar to the one we are experiencing today. Several ice cores have recovered Eemian ice, but it is difficult to interpret. This new map of the age of the ice sheet shows that there is more Eemian ice than expected in northern Greenland, where it may be easier for scientists to collect and analyze. This new analysis reveals a 3D map of the age of the Greenland ice sheet, from the oldest Eemian ice to the layers deposited during the last ice age, to the ice that formed during the Holocene. The response of the ice sheet to past climate change led to its current age structure. Further study will help us better understand how the Greenland ice sheet will respond to today's changing climate.
Okay, of course I don't quite agree with him because ice cores have the answer, while the radio echo sounding doesn't always map the very folded layers close to the bottom, so they don't get it quite right. But that's my interpretation. So I think I'll end this first case with the conclusion that the melt and the reduction of the volume of the Greenland ice sheet during the Eemian could contribute up to 2 meters of the sea level rise. But the interesting thing is that we, from many other sources, for example, from coral reefs in West Australia, see that the coral reefs, which is out on these platforms here, they're dead now, but we know they were alive during the Eemian, and they lay 3 to 4 meters above the present sea level. So based on observations like that all over the Earth, it's concluded that during the Eemian, the sea level was 5 to 9 meters higher than it was now. And this is serious, that's quite an amazing sea level rise. But I just told you that we only had 2 meters from Greenland. So even with thermal expansion and all the other things that can happen, we must have about between 2 and 6 meters from Antarctica. So there will be contributions from Antarctica into our future. And one of the things we are thinking about a lot is that if you look at West Antarctica, I'm losing my microphone here, sorry for that. You can see that there are areas where the bedrock, that's where the ice is standing on, is 1.4 kilometers under the present surface of the ocean. And of course, if you have a big piece of ice laying like that, and it starts to thin, at some time it will pop up and become an iceberg, and it allows to release a lot of ice from the ice sheet out into the ocean, can give this sea level rise of 2 to 6 meters. And we know this has actually happened in the past. We just don't know if it has happened during the Eemian. So we think it could be from West Antarctica, not West Antarctica, but it could also be from East Antarctica. So this is one of the things that we can learn from the ice cores, that we can get these very big ice, sea level rises from big disintegrations of the ice caps. My second example is looking at these abrupt changes you see during the glacial time, because this is something we don't see in the warm periods, but only when we go into the cold periods. And if we try to blow it up a little, and in this case we have made the blow up is the red curve there, and you can see here that we go from this end here from 58,000 years before present to 28,000 years before present. And you can see when you look at the red curve that you have a cold period, and then you have a very abrupt warming, and then you have a cooling again. And it happens in average every 2,000 years, and the warming can be up to 16 degrees Celsius over Greenland. Actually a lot more than we have right now. The interesting thing is if we compare them to the ice cores in Antarctica, which is shown with the blue curves here, you can see that they don't change as much, the wiggles are much smaller, and they don't look as if I plotted it in phase, but I have. So what you see is that the gray shaded areas, that when you have the very cold phases in Greenland, you can see you have the warmings in Antarctica. So you can follow several of them. It's cold in Greenland, and you see the warming in Antarctica. So what it shows us is there's an exchange of energy between the two poles. When it's getting cold in Greenland, Antarctica is warming, and the other way around. And this shows that there's some internal exchanges of energy between the poles that actually can give very dramatic climate changes on the different poles, but it has nothing to do with the solar irradiation. It's certainly internal exchange of energy. We've studied this a lot, and we think it's related to the collapse of the big ice cap covering North America, the Lorenz ice cap, and it's related to changing ocean currents and changing atmosphere patterns. But it's a super long story, so I won't give it to you here. I just want to show you this figure here, that if you plot the length of the cold periods in Greenland on the x-axis against the warming in Antarctica on the second axis, you can see that there's a very nice and linear relation. So this shows that there is some sense in what I'm saying. There is some physics related to the processes that are going on that are very important. We call it the bipolar seesaw. Now the third case I have to show you is what we learned from the air bubbles in the ice, because it is so unique that we have these air bubbles in the ice cores. So I just tried to make a first plot here from Antarctica, where you can see from an ice core in Antarctica how the greenhouse concentrations of CO2 for 10,000 in the year 1000, the concentrations was about 280 parts per million. And then when we pass about 1700, you can see how the concentrations of greenhouse gases increase. And now the values are up around 420 parts per million. The blue rings are the values from the ice cores, while the red curve is from Cap Grim when you started measuring the remote background concentrations of CO2. So you can see it fits together, but it also shows how short the direct observations are and how valuable the ice cores are if you really have to understand what is going on. We can do this for methane and other of the greenhouse gases, but of course we can also look back in time. And for once I've cheated, because I've taken a curve from Antarctica that's 800,000 years old. So 0.8 million years, that's 800,000 years ago. And then we go towards the present time. Around 0.1, we have the Eemian and the cold period and our present Holocene that I've been talking about before. When you look at these curves, you can see that the temperature, the red, is waxing and waning into glacial and interglacial time periods, with a period around 100,000 years. But when you look at the greenhouse gases, the CO2, you can see that there's also a change, natural change of greenhouse gases during the pre-industrial time. But nowhere, no time do we reach values as high as 420 parts per million as we have right now. So clearly, there's a very strong man-made signal in our more recent years. And just to come with an example, I found these curves here for the more recent years. And I want to note that we had COVID in 2020 and 2021. So you can see the top curve there. You have the annual cycle of CO2, and then you have the mean values, which is the black curve here. And you can barely see that COVID has been there. You can't see that the industry shut down, that the planes were not flying. And it's even more evident on the curve to the bottom, where you can see that 2020 is the red curve, and you can see the drop of emissions in the spring of 2020. But you can see even with this drop of emissions, it's nearly nothing. And this actually shows us how big actions we need to take to reduce the emissions of greenhouse gases, which we really need to do. So that was this case. So I've talked about 3 cases. I talked about what happens when it warms during the Eemian, how warm it can be. I talked about the abrupt climate changes during the glacial, where we have warmings lasting not more than 100 years, up to 16 degrees over Greenland, not globally. And I've talked about how the greenhouse gas values are getting really high. So when the last climate report came out from the IPCC again, showing what can we expect of sea level rise, they brought this ensemble of curves there. Then we were 29 climate researchers that wrote a letter to them and said, we don't think they had taken under consideration what happened in the past and the risk of what happens when you look for a longer period than 140 years where we have weather station data. Because that's actually a really short time we've been observing our climate. And then they added this dashed line, which they call a low likelihood, high impact curve, based on the knowledge what could happen in the past. So this is based on the paleo data that they see that there is a risk for a higher sea level rise if we take some of the processes into account that we've seen in the past. So this kind of ends my story about what I can expect that can give abrupt changes in our future. If we can reduce the ocean currents by releasing a lot of fresh water into the ocean, and this would probably cool the north and warm the south, as we saw during the glacial time. We can get an abrupt sea level rise if we get a disintegration of the ice in West Antarctica, because the sea level rises and triggers this abrupt change. And finally, the very high concentrations of greenhouse gases will probably warm our climate more than 2 degrees. At least me personally, I think we have reached this point where we cannot, reduce the change to the 2 degrees that we really wish to do. So this ends my climate story, and I'll tell you a little and show some pictures about the camp where we're drilling the ice core right now. And while this movie is running, I'll tell you that each year Greenland receives 650 billion tons of snow as snowfall over the ice sheet, but then it loses 820 billion tons of ice, half of it by melt along the margin of the Greenland ice sheet, and the other half by the ice streams that are discharging ice into the ocean. And this discharge of ice is probably the thing we don't understand in the climate system. How do these ice streams work? And this has been the motivation to drill an ice core in the middle of the big Northeast Greenland ice stream that we also call Negis. So we started this project by moving our camp from our previous site to EastGRIP in 2015. And in one of the first slides, you saw the building of this big dome, our main structure. But you see, we built it on plywood standing in the snow. And we decided it would be very nice if we could move this dome with us to the new site. So we asked a company in Germany, and they made a platform for it. And they said, now you just need to bring in a crane so you can lift the camp. I said, no, we can't do that. And then we asked our Icelandic friends, and they said, you just have to make a ring, the blue ring, and couple it to all the legs. I think we did that with several hundreds of balls. And then you place the foots for the skis, and then when the skis are on, then you cut the legs, and you have your dome on skis. So this is what we did. We got the big skis to camp. You can see them there. And we put them down the ramp under the dome and mounted them and cut all the legs. And I was actually sitting in the dome when we got the big, when the legs were cut. But it all worked very well. So finally, we got the dome on skis. I think it was only about 30% of the camp that actually believed it was possible. And I'll show you a little movie here of a case that first it's pulling out a winch, the yellow one in the back, and then it's blocking the wheels, and then it's trying to winch the dome into action. So you can see in a second what happens, that it sets in the snow, and then it actually managed to move the dome over the surface with the generator in the white box in the back and a fuel tank afterwards. So this was a very comfortable traverse over the ice, like bringing your own snail house with you. So you can see here a few pictures from the dome as it moves along in a second. That's pretty amazing, yeah. So this is inside the dome where we have the living, the offices and the sofas. This is under the dome, and you can see the wires that are coupled from the center out to the ring. It's actually the biggest bicycle wheel you've ever seen because it's a very, very strong structure to make a bicycle wheel. So you can see it all worked well. In 10 days, we moved the 400 kilometers over the ice and started to establish the new camp. This is our parade picture. You can see there in the bottom. You can see there's no footprints in the front. We've been very careful. So you can see the dome with the case, and you can see our 2-piston pulley taking the equipment, and you can see our smaller flex moving other structures. And you can see 3 skidoos, because of course we had to drill a few ice cores and make a little science on this move. So we did that on the way. Then we started to establish camp in 2016, and we decided that we would not make the traditional trenches with wooden roofs. We would try a new technique where we would inflate big balloons and put down in the trench and then blow snow on top. I'll just show you the big balloon here. It's 40 meters long, and it has a diameter of 5 meters. And if you've been in Copenhagen and you've been with the metro in Copenhagen, exactly the diameter of the metro tunnels. So I encourage you to sit you in the front and you'll enjoy thinking about the tunnels if you run with a metro. But if I go back, here you can see the tunnels. We've made the tunnel systems with an inclined trench going down, and then the drill trench, and a staircase as safety in the vertical shaft. We have 2 side trenches, one where we log and preserve the ice cores. Then we have a science trench and a storage and a place at the end for the packed ice core boxes, and then we have a lift going up to the surface, so there's no risk of us dropping the ice core, the very valuable ice core boxes at the end. So it worked very well, and we managed to drill the ice core. Actually, we reached the bottom this summer at a depth of 2,670 meters. We did a lot of great science. We had a lot of young people in the camp. And I'll just end showing you a little movie that's made in red light, and then I've turned it gray, because we're to preserve the rocks and grains in the ice core. We use red light so we don't destroy the luminance measurements. So it's not, the pictures are not so nice. But
a lot of small stones and mud mixed with ice.
Yeah.
And it was very hard to get this last core up, also to get it out. So I think that we were not able to drill any further with the rock drill here, because it's literally melting away, and this mud is it's not easy. It's very hard to drill with this rock.
I think this is the mud that the whole ice stream is sliding on. So we're simply down in the mud under the ice. Who would imagine it would look like this?
So. I mean, we have drilled now 4 meters longer down than where we expected the pressure melting point, and now this is what we get. So I would say this is the end of the line, half of our drilling.
This is amazing. It's very beautiful. Yeah. Thank you very much.
It's been interesting.
Good long.
Very exciting. So and we almost had a hard time to even bring this up, as you know. So this is a good time to stop for now.
I think we need to go up and get a glass of sparkling wine.
That would be highly appreciated.
Sure.
Okay.
Okay, let's save that and get it into the cold. Okay, so that was a wild movie made at 2 o'clock in the night in red light. And the drillers left camp the next morning, so it was kind of a miracle we actually made it. We'd had a lot of problems and had a lot of stop drills, and we understand that it was because the drill was down in the water under the ice. And when you try to to pull something up that's stuck in water, it's kind of like suction. We can't get it free, and that's what happened. But we got a lot of ice cores up with basal material. We got some rocks up, and we didn't get gold up. It's a part of the drill that has been broken off, so no gold under the Greenland ice sheet. And so that's been very successful, and I think you're between the first that we share this story with. So with that, I'd like to say that one of the greatest pleasures of doing this project is that we can bring so many young scientists to the camp. More than 50% are young and emerging researchers from 14 nations that being together in the camp form a network for the rest of their career. That's really great. So that I'd like to thank you and ask if you have questions for me. Thank you very much.
Thank you, Dr. Dahl-Jensen, for the fascinating lecture. So now to moderate the Q&A, I'm going to welcome Dr. Raphael Ferrari, who is the Cecil and Ida Green Professor of Oceanography and co-director of the Lorenz Center at MIT's Earth and Atmospheric and Planetary Sciences Department, who will serve as moderator and join Dr. Dahl-Jensen up at the table here.
Well, first of all, thank you for a wonderful, educational and inspiring lecture, Dorthe, and I think I share the same sentiment with the whole audience, and now we want to start asking for your questions. I'm sure that there are many, but we'd like to start with the pre-college students, if there are any in the room. If anybody's brave enough to break the ice. Otherwise, maybe in the meanwhile, I'll start asking my own question. And I'm not pre-college, but I'll take the liberty. I want to ask, you spent a lot of your career looking at these records. If you had to go back in time and see what was the biggest surprise that you find by looking at these records, something you really didn't anticipate?
Well, I think the first times we saw these big abrupt changes during the glacial times, where we could see all our parameters jump on just a small piece of the ice core. I mean, that was unexpected and very, very fascinating. And it's taken many years, many ice cores for us really to understand it. And also collaboration with all other partners within Earth science, ocean modeling, atmosphere modeling, ice sheet modeling, to understand it. I think that's been super fascinating. I don't even think we can claim we know everything yet.
Okay, we have a question here.
What was your power source for all this?
I'll repeat the question because I'm not sure online they hear. What was the power source for the amount of energy? It's pretty substantial to do all this drilling.
When we saw the dome move over the surface, you could see there was a white box on sledges behind the dome. This is our main generator that we have put in an isolated box so it doesn't make so much noise. And also so we can use all the waste heat to warm the dome and melt the water we use in the camp. But it's a generator.
Was it diesel or?
Yeah, it's a diesel generator. Actually, we bring in Jet A1 that we can use for the aircrafts, and then we put some oil in it so it can work as diesel.
More questions from the audience over there.
How do you estimate the temperature 100,000 years ago based on your core samples?
So how do you reconstruct temperature from ice core samples?
My old professor, Willy Dansgaard, was the first who invented the method of measuring the stable water isotopes. So basically you look at the water molecules that has an oxygen atom, and then it has two hydrogen atoms as well. But the oxygen can have the atomic weight of 16, 18, and 18, but also 17. But we measure how much oxygen 18 there is compared to 16, because it's a function of how much of the original precipitation is left in the cloud, which tells us what the temperature of the cloud is. So that's what we do.
Lady over there.
How do you quantify the amount of CO2 or other
So how do you estimate the CO2 concentration now in the air bubbles?
I mean, first of all, CO2 is very, very difficult because as long as there's any water close by, it changes its properties. So we do what we call a dry extraction of the air bubbles. So we keep it frozen and put it into a little chamber, and then we pump the air out, so there's vacuum, and then we have, you know, two kind of needles. We punch through it, so we punch the air out of the bubbles. Then we pump the air out, and then we clean it and other things. Then we use a mass spectrometer to measure it.
More questions? Here, Neil.
I want to make sure I understand this correctly. Over 120,000 years ago, we were at least 5 degrees C hotter for 6,000 years, and we only got 5 to 7 meters of ocean rise out of that?
That's right. That's right.
So
and
the question is about the sea level rise in the Eemian and what might tell us about what is happening in the near future.
Yeah, that's right. And I mean, we understand why it was warm during the Eemian because it's due to the position of the sun and the Earth. That's a position where we receive more sun on the high northern latitudes. And so in that way, we had the melt. But it is true, it is nice to hear that we can receive so much heat for so long time and still only have a sea level rise of 9 meters, which though I would say it is pretty serious.
Another question over there.
Are there any plans in place to prevent this?
So, okay, and this resonates with a question also online. They're asking whether there are geoengineering solutions that might prevent the melting of sea ice, or there are ways to prevent it.
Well, there is a lot of attempts for geoengineering, and I don't know about all of them, but one of them I know about is if you have a coal production of energy, you can take out the CO2 in the chimney, where before it's released to the atmosphere. And by that you use, I think, 1/4 of the energy to capture the CO2, but you can make clean energy in that way. There are other methods, but to my knowledge, I think nothing is easier than not releasing it.
Any more questions? Over there.
Are there differences in the Antarctic to the ice cap in Greenland?
So are there fundamental differences between the ice caps in Antarctica versus Greenland?
Yes, there is. I mean, it's all ice, that's for sure. But in Antarctica, the ice in general is 10 degrees colder. It's placed much colder. And that's, of course, also why it's not reacting so much yet. Another difference is that while the snowfall in Greenland gives, if you take the snow and compresses it to ice, we have each year is like 20 centimeters near the surface of the ice cap. In Antarctica, because it's colder, it snows much less. So each layer is only about 1 to 2 centimeters of ice. So it's all been mixed, so you never have the annual resolution we have in Greenland in Antarctica. And because it's so cold in Antarctica, you don't have very much melt around the margin, but you have enormous ice streams going out in ice shelves, and this way discharging the ice from the ice sheet. So there is some fundamental differences between the two ice caps or ice sheets.
Are you a bit jealous that in Antarctica they get longer records though?
No, not at all, because we are drilling an ice core in Antarctica right now as part of the European project called Beyond Epica Oldest Ice, where we're going to drill, also with the Danish drills, next year. We will probably reach bedrock and get 1.5 million years old ice. So that's a new story to come.
Question over here.
Okay. Over polar regions, you get 2 to 3 times the delta T that you get in terms of a global average. And if you could reduce that to, say, 1 times, you would have much less sea level rise, much less melting from Greenland and Antarctica. And there was an Australian guy who was pushing a proposal to get rid of cirrus clouds over polar regions only. He was saying that there were chemicals that would disperse them that would not diffuse over other latitudes. Are you familiar with that at all? Do you have any comment on that?
So I guess the question is, given polar amplification, are there any ways to reduce the warming at high latitudes in particular?
I must admit, I don't know enough about this method to kind of tell you about it. I just know many of the methods to reduce clouds is methods where you have to continue doing it every year. As soon as, I mean, mostly it's a kind of releasing some kind of impurities in the atmosphere to resolve the clouds. But you have to do it every year. So you have to continue to do it. Yeah.
We're only trying here to cirrus clouds.
Yeah. But I mean, I think, if it works, it would be a really good idea. Yeah.
There is a very interesting question online. It said, if we could magically remove all Greenland ice in the present-day climate, would it just regrow?
No, as the ice cap is now, it would not regrow because then the base of the ice would be down close to sea level. And at that level, it's melting right now. It's annual plus temperatures. So you would not be able to rebuild the ice sheet if it didn't get at least 10 degrees colder.
A question over there.
In the last video you showed, you said it was surprising that this ice was sliding on mud. Why is that surprising, and what's the significance of that?
So the question is, why is it surprising that the ice would slide on mud?
When we didn't really know how an ice stream was really moving. And if you read many of the textbooks, you learn that you have a surface velocity, and at EastGRIP it moves 58 meters every year. But then the basal sliding is 80% of the surface velocity would be around 42 meters per year. And then there would be a shearing layer where the velocity moved from the base to the surface velocity. So we were always expecting to get into this shearing layer, and we were very worried about our drill if it would get stuck at the bottom. So in that way, it was a surprise we got through the whole ice stream without seeing any change of velocity from top to bottom, that it's all sliding over the bottom. But I agree with you, what should it slide upon? It would probably be water and mud. We're just standing there at 2 o'clock in the night, and we got all this water and mud up, so wow, this is amazing.
Yes, one last question over there.
What material was that large balloon made out of?
What material was the large balloon made of, the one used to build the structure?
Well, I think it's just made of rubber. It's a company in Denmark that makes big balloon for beer production, because you release a lot of CO2 when beer is produced, and then you pump it into the beer at the end. But I think they've never made such a big balloon, because it's actually their picture, and they put it in the local newspaper because they were very proud of having made this big balloon for us.
Okay, I think this brings this evening to a conclusion. I want to thank again Dorthe. What a wonderful lecture.
And I'd like to thank you all for attending and coming with so many great questions. Thank you very much.
Yes, and Dorthe will be down here for a while, so if you have more questions, please come down.
I'll just tag on to that just real quick, and just to thank Doctors Ferrari and Rothman and the Lorenz Center in general for their partnership on the John H. Carlson Lecture. This being, what, 13 years? Was that correct? 13 years in running. Thank you for everybody for coming out. And I also just want to reiterate our gratitude to the Lowell Institute for the support they provide our lecture series at large, allowing us to offer these lectures free to the public. As was noted, you can come down here to the podium, but we would encourage everybody to kind of congregate out in the lobby. We're going to have coffee and tea, which will remain open until 8 for the next half hour or so. For those that joined us virtually, thank you for the great questions and for joining us. And our next lecture in our fall lecture series is November 13th, as I noted earlier. We're going to be welcoming a social entrepreneur, Daniela Fernandez, who she's the founder and CEO of the Sustainable Ocean Alliance, and she'll be joining us to talk about her work and their amazing work around innovation to safeguard our ocean. So please join us then, and good night, and thank you for coming out.